Right, after looking at logarithms yesterday, what we're going to do is concentrate our attention today on solving exponential equations and inequalities. So a common technique that is used when solving exponential equations and inequations is to equate the bases. So here's a situation where I might consider equating the bases. So I've got 4 to the x equals, okay, and what I attempt to do is make this right-hand side fit kind of in inverted commas the template. So this raised to this equals this raised to this, where I've got the same base on either side. And that means that I can just simply equate the powers. All right, so let's get these, or attempt to get these into the same base. So this is 4 to the x equals, and I need to write this as base 4. Okay, so I believe that this will be 4 to the 4. Okay, now how do I know that? Well, I know from experience now, hopefully you've seen 4 to the 3 a few times, is 64. So 64 times 4 is going to be 6. 6 4s are 24, 25. That's 4 to the 4. Okay, so that would be expected of you. That is a fairly entry level kind of exponential for year 11, year 12. So practice these and maybe write some of these common base and power combinations that you see down. Okay, so that means that x is equal to 4 in this case. All right, now let's go over to this one here. So I've got 5 to this and 25 to this. Now note that 25 can be written as a base 5. So I'm going to rewrite the left-hand side, or leave it as is. Rewrite the right-hand side as 5 to the 2 to the negative x plus 2. All right, that's one power raised to another power. What I do is I multiply the powers. Negative 2x, what's that, plus 4. And now, because the bases are the same, I'm going to equate the powers. 2x take 4 equals negative 2x plus 4. All right, I've got 4x equals 8, x equals 2. Now, involving quadratics. So solving indicial, I can't even say that word, indicial equations involving quadratics. There is often a hidden quadratic in some exponential equations you are being asked to solve. So these, again, come up a lot in Year 12 methods exams, the hidden quadratic, okay? So identifying the hidden quadratic is really, really important, okay? Now, here's the classic one that comes up is in this form here. So you want to solve this, and what you would do is attempt to equate the bases or whatever. It's just not going to work. It just won't work for you. Okay, so the method we're going to use is to see if we can identify the hidden quadratic. So here goes. What I'm going to do is rewrite this with a base 3. Okay, so that's 3 to the 2 to the x equals 12 times 3 to the x, take 27. Don't know. All right, I'm going to just swap the x and the 2. This is multiplication, so I can do that multiplication whichever order I want. So 3 to the x to the 2 equals 12 times 3 to the x, take 27. All right, now, I don't know, still none the wiser. But here's a move I'm going to do. So see if you can see if you're happy with this. So I'm going to say that a equals 3 to the x. Why? I don't know, I feel like it. I'm going to let a equal 3 to the x. So let's use the word let. All right, so wherever I see 3 to the x, I'm going to replace it with a. A squared equals 12a, take 27. Hello, that's a trinomial. Okay, so what I'm going to do to solve the trinomial is pull everything over to the left-hand side. A squared take 12a plus 27 equals 0. Now I'm going to solve this using my known methods. Excuse me. So I've got 9 and 3, a, both neg. A take 9, a take 3 equals 0, a equals 9, a equals 3. Now, many students leave it at that or go, that's my answer, a equals 9 and a equals 3. Well, what am I trying to solve? I'm trying to solve this. That is solving a quadratic. Now, what we need to do is sub the 3 to the x back into this to finish the job off. This a substitution simply allowed us to further engage in the problem. Now we've got to bring it back in and solve the original problem that we were trying to solve. So I'm going to say that 3 to the x equals 9. Okay, so I've subbed for a there. and I'm going to say that 3 to the x equals 3. Right, both of these I can equate the bases on. So this one here is going to be 3 to the x equals 3 to the 2. This one here is going to be 3 to the x equals 3 to the 1. Same bases, that means x is equal to 2 and x is equal to 1. Okay, so there are two solutions. Now make sure you go ahead and check those to make sure that they're both appropriate. Yep, in this case, no worries. All right, let's do this one here. Again, this is a hidden quadratic. This one here can be rewritten as 3 to the 2 to the x equals 27 take 6 times 3 to the x. And again, we're going to use the same technique that we used there. So we've got 3 to the x to the 2, take 27, take 6 times 3 to the x. Now let's go let a, or whatever letter you want, equal 3 to the x. A squared equals 27 take 6a. A squared plus 6a take 27 equals 0. All right, 9 and 3 x. One of them needs to be negative, and that is the 1. Right, x, not x, my bad. A take 3, a plus 9 equals 0. All right, a equals 3, a equals negative 9. All right, let's make the substitution. So I've got 3 to the x equals 3, or 3 to the 1, in which case x is equal to 1. I've got 3 to the x equals negative 9. All right, now here's an interesting conundrum or problem, okay? Now the graph of 3 to the x, so y equals 3 to the x, looks like this. And we want to know when that graph will equal the value negative 9, okay? When do you think it's going to happen? If your answer is never, that's correct. So 3 to the x is actually never going to equal negative 9. And the other way to think about this is 3 raised to what power will give me a negative number? Well, 3 raised to any number in the real number system will always produce a positive value. You can never get a negative, okay? So we're going to say that 3 to the x can't equal negative 9 as 3 to the x is greater than 0 for all x. Okay, so this problem here only has one solution, x is equal to 1. And again, it's important to then go back and check your answers. Don't just get these values here and just say that they're mathematically true. All right, some inequalities. We've got 16 to the x equals greater than 2. So I'm going to try and write this to the same base. So that's 2 to the 4 to the x greater than 2. That's 2 to the 4x greater than 2 to the 1. That means 4x is greater than 1. X is greater than a quarter. No probs. Okay, over here I've got 2 to the negative 3x plus 1 less than, I'm going to write that as 16 to the negative 1. 2 to the negative 3x plus 1 less than 2 to the 4 to the negative 1. 2 to the negative 3x plus 1 less than 2 to the negative 4. Same base, equate the powers. Negative 3x plus 1 less than negative 4. Negative 3x less than negative 5. Divide by negative 3. Ding, ding, ding. Dividing by a negative means we have to flip the inequality to continue or to make it true. X greater than 5 on 3. All right, Cambridge has got this particular exponential inequality problem that if your x is greater than y, then blah, 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 then flip. Oh, I don't even know what the hell this means, okay? So what we're going to do is just use a little bit of common sense in some scenarios. All right, so if we were to solve this, we've got half to the x, and I want to know when that's greater than half to the 3. And you might think, well, same base, equate them, x greater than 3. So this seems to suggest that this graph here will be more than what this is, which is 1/8 for all the values of x greater than 3. So let's find out where 3 is. There it is there. All right. And what do you notice? That for all the values of x greater than 3, it looks like it's less than 1/8, not greater than 1/8. Okay, so what would I have to do to make this true? Well, I would have to flip this inequality. Now, why do I have to flip it, or how do I know I have to flip it in this scenario? Well, here's your best bet. Don't do it like this. Rewrite all of your bases, not as fractions, okay, but as using the negative index rules. So again, what I'll do is I'll just step this through to show how this comes out. So if our problem is half x greater than half to the 3, what I'm going to do is say that this is 2 to the negative 1 to the x, 2 to the negative 1 to the 3. Let's use power to power rule. Negative x greater than 2 to the negative 3. All right, same bases. Negative x greater than negative 3. Divide by negative 1, divide by negative 1. Dividing by negative, have to flip the inequality, x less than 3. So if you do that particular method there, that overcomes you having to be able to, one, understand what the hell this thing is talking about, and two, saves you from memorizing it. Oh, when I've got a fraction base or blah, blah, blah. Okay, so use negative index rule to help you out with those ones. All right, there's 13D. Do those questions, please.